Amides aren't the only types of fairly resistant carboxylic acid derivatives. Nitriles also aren't terribly electrophilic, but they can also be reduced with things like lithium aluminum hydride. Last class or previous classes we saw that we can already reduce nitriles with diol. The reduction with lithium aluminum hydride ends up going a little bit further, where we're going to end up fully reducing this to a primary amine. So once again, we're going to end up with both hydrogens from lithium aluminum hydride added onto this central carbon. This is going to occur in a similar fashion to all of our aluminum hydride additions, where this is a very good nucleophile. It'll directly add in to the pi star of this carbon-nitrogen triple bond. We make an intermediate carbon-nitrogen double bond that has an aluminum hydride intact. So now we end up having an aluminum hydride that still has active hydrides. These are still quite nucleophilic, and they're very close to this electrophilic imine carbon-nitrogen double bond. So we can imagine this attacking this intramolecularly. This gives us our second hydride addition. So both of those hydride additions came from the same original lithium aluminum hydride molecule. And we get a nitrogen that seems fairly unhappy. We have this. We always think about when we have a nitrogen that's deprotonated to be very, very basic and very, very reactive. This is somewhat tempered a bit because right next door, this aluminum has an empty p orbital. So you can kind of think about having stabilization from that empty p orbital to accept some of this electron density and almost make an aluminum nitrogen double bond. So this will now satisfy the octet on aluminum. Nitrogen is still here. And then on workup, you add some water, and we'll be able to break the nitrogen aluminum bonds and protonate the nitrogen overall. Revisiting the diol mechanism, we remember that after workup, we end up making aldehydes. And the first step of this is having the lone pair of the nitrile react with diol. Each of these R groups are isobutyl groups. So it attacks the empty p orbital. So first we have essentially a Lewis acid combined with a Lewis base, and this will give us an intermediate complex that is available, or I'll define this as a methyl just so we don't have too many R's running around. We have an activated species where now this aluminum hydride becomes more nucleophilic. The nitrile becomes more electrophilic. This can attack in. And we make this intermediate that is very much protected from further attack. So the aluminum does a few different things here. These R groups are quite big and bulky, so another diol molecule is unable to coordinate to this nitrogen atom for a secondary attack. So more or less it just kind of stops here. And the last step will be workup. So workup with water will first give us a plain imine. So it'll break the nitrogen aluminum bond. And then further workup with water is going to just be an imine hydrolysis, where we'll be protonating the nitrogen of the imine, having water attack, making the nitrogen a good leaving group through further proton transfers, and eventually getting us to an aldehyde. And this is an equilibrium process that'll be highly favored. All the ammonia that leaves will actually be leaving as ammonium, because it'll get protonated in the acidic media, so you don't really have the equilibrium backwards anymore. Nitriles can do other cool things. Actually, turns out to have a very nice ketone synthesis when you react Grignard reagents with nitriles. So if we were to add methyl magnesium bromide followed by workup, we end up making a methyl ketone. Where if you used a phenyl Grignard, you'd end up with a phenyl ketone. So this ends up being a new ketone synthesis. We don't have many of those yet. This is actually pretty useful all around. So we look at the overall reaction, can draw out methyl magnesium bromide. Again, we have a nucleophilic sigma bond. It'll attack the electrophilic pi star of the nitrile. This gives us first intermediate that does not undergo any further reactions. So we will stop here. No more additions after this place. So if we can think about the nitrogen-magnesium bond as being fairly ionic, we can kind of imagine this being something like a nitrogen minus with an MgBr cation. And so if we were to go and add in another nucleophile to this, it'd be similar to putting two negative charges on nitrogen. And we already know that one negative charge is hard enough on the nitrogen. Having two of these MgBr positive charges would simply just be way too high in energy and unreasonable. So this is not an addition we want to make. This is something to not do. Do not do this. And once again, if we work this up with mildly acidic aqueous conditions, we will first be protonating the nitrogen to make an imine that then, with more acidic workup, will convert the imine to a ketone in the same fashion as we had in the case of diol reductions.